Hello, Matt Johnson here. We're going to talk a little bit about the Lewis diagrams and Lewis structures. And these were created by Gilbert Newton Lewis at the University of California at Berkeley, a very influential chemist from the early 20th century. He also gave us Lewis acids and Lewis bases. He was the first one to use the term photon. Clearly a very talented guy. But the thing here is to think about valence electrons. And so Lewis was thinking about how the outer shell of electrons were responsible for giving them the structure that they have. And he invented a system for describing this. And so if I go over to the paper view, I can just tell you a little bit about Lewis's system. And let's see, let's start out with a very simple example. We'll just take carbon dioxide. And so the first thing you need to do is identify the valence electrons. Valence electrons. We can do that by considering the electronic configuration of the atoms involved. For carbon, we have 1s, 2, 2s, 2, 2p, 2. And I need to just sharpen the pencil a little bit here. Sorry. Just go weak, 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 weak. There we go, nice and sharp. So I'll set this off on the side. So we have the outer shell electrons. Call them the valence electrons, as opposed to the inner shell electrons that we are not going to consider. So that inner shell is out of the game. We also have oxygen atoms in our carbon dioxide. Electronic configuration is 1s, 2, 2s, 2, 2p, 4. And there it looks like we have a total of 6 valence electrons, not considering the inner shell. So here we have 4 electrons, here we have 6 electrons. And then since we have a second oxygen atom that also has 6 electrons, this looks like we have a total of 16 valence electrons to work with in the system. Now, the thing that Lewis did was to identify the Octet Rule. And it said that each element would like to achieve an octet of electrons, valence electrons, through bonding. And you can see here that carbon only has 4 electrons. Therefore, it has a deficit. Deficit for carbon would be 8 minus 4 is equal to 4. For oxygen, we would have 6 minus 4 is equal to 2. This means that carbon would like to form 4 bonds in order to achieve an octet. Oxygen would like to form 2 bonds in order to achieve the octet. Now, one way of doing this would be to have 2 bonds on each oxygen bonding with the carbon, giving carbon a total of 4 bonds. We would have something that might look like this, that achieves this rule. That would be using up, you remember that Lewis told us that a bond is made up of 2 electrons in a spin pair, right? So this is a valence bond, 2 electrons in a spin pair. So now we've used up 2, 4, 6, 8 electrons. We have a total of 16 electrons. That means we should add 8 more electrons. And why don't we put these on the oxygen atom, since oxygen is pretty electronegative, right? So we could go like that, and that, and that, and that. And so then we need to check if this is a good structure according to Lewis. So the first idea is the Octet Rule. And then we just need to find out if we have a total of 8 electrons from the lone pair and the bonding electrons. And it looks like this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. That's good. That's the same for this oxygen atom. That's also happy. And then we can get a new pencil from over here. this carbon atom looks like it's going to have 2, 4, 6, 8, so it also obeys the octet rule. And then there's a kind of a rule for valence charge. And this says that we can divide each bond in half. And then find out if that balances the number of valence electrons that we expect. And for example, for carbon, we would want to have 4 valence electrons, and we split these in half, so we have 1, 2, 3, 4. That's great. Valence charge is satisfied. We already knew that the octet rule was satisfied. We can check the valence charge for oxygen. Again, we split those bonds in half. We have 1, 2, 3, 4, 5, 6 electrons. That matches what we would expect, and therefore we get a second smiley here for each oxygen atom. The third smiley, carbon, oxygen, oxygen, all are obeying the valence charge rule. Okay, there's a special condition to the octet rule, and this is in the case of hydrogen. Hydrogen is quite small. The electronic configuration is just 1s1. The p orbitals haven't opened up yet. It only has space for 2 rather than an octet. So if we take, for example, methane, we would like to have something that might look like this. And there's a few things going on here, right? So hydrogen obeys the octet rule because it achieves these 2 electrons by having a bond, right? It starts out with 1, but it's able to achieve and satisfy the rule by forming a bond with carbon. That's really good. It also obeys the valence charge rule because if we split this in half, we have 1 electron that corresponds to this electron. Really good. We're also obeying both of these rules for the carbon atom. It has 2, 4, 6, 8 bonding electrons and lone pair electrons. It doesn't have in this case, but it's obeying the octet rule, and it's also obeying the valence charge rule by having 4 electrons in all. Now, I drew this 3-dimensionally as a tetrahedron because I was thinking that these electrons and these bonds might like to get as far away from one another as they possibly can in order to minimize the electrostatic repulsion. This is actually the valence shell electron pair repulsion, or VSEPR theory. And this says simply, you know, as we saw here, these things would like to swing away from one another in order to reduce the electrostatic repulsion. And that gives methane a tetrahedral structure. And we could go back and apply this simple rule to carbon dioxide. Valence shell electron pair repulsion. And this means that carbon dioxide is going to have, oh my goodness, let's start that over from the top and make carbon dioxide linear. Experiment shows that that is the case. Carbon dioxide has a linear structure. All right. Now we're going to go back to this view. Hi there. So Lewis was nominated for the Nobel Prize no less than 41 times, in part for this paper from 1916 describing the structure of molecules. And he never won the Nobel Prize. Some people say that this was because of a feud he was having with Nernst, and that Nernst had friends in Sweden who were on the committee. But it's undeniable that Lewis has had a huge influence on modern day chemistry. He was the advisor or the mentor to a lot of people who went on to win the Nobel Prize. 5 very close co-workers of his won the Nobel Prize. This was Harold Urey, William Joke, Glenn Seaborg, Willard Libby, Melvin Kelvin. And we're going to develop a lot of these theories more as the course goes on. So I'd like to close by giving you a bit of advice and a bit of a warning. Never trust an atom. They make up everything. I'm Matt Johnson. Goodbye for now.